This week we're talking about statistical tests, and today we're focusing on confidence intervals. Well, last time I outlined confidence intervals as an alternative to hypothesis testing, many of the same concepts that hypothesis testing uses, such as estimating a mean or other parameters of a distribution, also come up and apply for hypothesis testing. First, I want to be very clear about a fundamental assumption that we're going to make both now and for hypothesis testing with continuous distributions. We're going to assume that we have numbers that come from a normal distribution. This is not a crazy assumption. One of the most important theorems in mathematics, the central limit theorem, says that if you sum enough draws from any distribution with finite variance, it will look like a normal distribution. This is not a stats class, so we won't talk about how to check if something is actually a normal distribution. Although you can use something like the chi-squared test we'll talk about later to check, you should do some sort of check, even if it's just eyeballing the data, to make sure it kind of looks like a normal distribution. It's often a very reasonable assumption, but it's an assumption that everything afterward depends on. We'll come back to an alternative in a bit, but for now, just keep in mind that everything we do assumes that our underlying data come from something that looks like a normal distribution. Okay, so let's say that you have some data from a normal distribution, but you don't know the parameters of the underlying distribution. How would you find the mean and variance of that normal distribution? The mean is what you'd expect from grade school arithmetic. Add everything up and divide by the number of examples. The estimate of the variance, however, is a little more complicated. Once you have an estimate of the mean, you need to see how far all of the observations are from the mean, square it, divide by n minus 1, and then take the square root. And that gives you the sample standard deviation. And the standard deviation is the square root of the variance. So if you square this, you get the variance that we talked about last time that describes how spread out a distribution is. Another difference, which is more of an aside, is that this is an unbiased estimator for the variance using Bessel's correction, which we won't prove in this class. The maximum likelihood estimator divides by n, which is typically not used for confidence intervals and statistical tests. Let's also take this opportunity to discuss different ways of specifying the variance of a normal distribution. Let's go over the options. There's the variance, which we typically write as a Greek letter sigma squared. We talked about the variance before as a parameter to the normal distribution spread. There's the standard deviation, which is the square root. When we compute the sample standard deviation here, it's often represented with a capital letter S. In computer programs, where you often have a PDF for many different distributions, sometimes the variance is called the scale. So now let's look at some data. In this case, the ages of presidents when they were inaugurated into the office of President of the United States of America. We can apply the formulas on the previous slide to compute the mean and the sample standard deviation. Let's go over what this would look like in Python. We first have to import a bunch of stuff as usual. We're going to use a new package called pandas for reading in the data from a CSV file. This is all in the warm-up directory. So let's compute the mean and the sample standard deviation. Let's plot what the PDF would look like. It's centered at the mean, 55, and extends out from that. We want an interval. That is a minimum and maximum value that would have 0.95 of the probability mass between those two endpoints of the interval. To figure that out, we can use the interval function and provide it the mean and the scale, which is the sample standard deviation. So great, this gives us the interval from 42 to 68. We can be reasonably confident that a president's age is within that range. You'll often want to be more certain. To do that, you'll have to have more observations. In the case of American presidents, we'll just have to wait until a new president is elected. But for data you do control, sometimes you can gather more data. This is clearer if we look at the case with a known variance. The 0.95 confidence interval is 1.96 times the standard deviation divided by the square root of the number of samples. So the more data you have, the tighter your intervals. The probability of a president being less than 35 at the time of inauguration is 0.1%. while the probability of being less than 0 is 10 to the negative 17. Small, but not 0. And let's be clear, this doesn't make sense. The Constitution prevents people under 35 becoming president, and certainly people have to be born to be president. So the normal assumption isn't completely justified. And when I say normal assumption, I mean the probability that the distribution is a normal distribution. However, sometimes the assumption is reasonable enough, as it is here if you actually plot the ages. It is pretty clustered around the mean and spreads out in either direction. Sometimes, though, you want to test the effect of one thing on another and compute a confidence interval based on that. Let's take an example from deep learning. Deep learning systems are dependent on the data that they're trained on. How they're related is complicated and non-obvious. You might reasonably want to see how sensitive your system is to the data. Let's say that you want to compute a confidence interval of the accuracy of a deep learning system trained on some collection of tweets for sentiment analysis or something like that. This is called a Bootstrap Sample. It's a handy, elegant, but often computationally expensive way of computing the uncertainty associated with something that you don't quite understand the complexity of. So you have a pool of data. You sample with replacement, so you could have 2 draws of the same example from your data. You train your complicated system, and you compute some statistic, then you repeat. You again sample with replacement a subset of your training data, retrain your sentiment classification system, compute a parameter, and repeat. And then you get a sense of the distribution of what is the accuracy based on the variation of your training data. Now that we've talked about confidence intervals, we can move on to comparing distributions with statistical tests and deciding, for instance, whether 2 sets of data are substantially different. If you want to see more videos like this, check the video description for the course that comes from the link down below. You can then see the context and the correct order for watching these videos. YouTube will gleefully show you stuff in the wrong order. If you want other people to see this video, provide a big gradient to the recommendation algorithm by clicking the like and subscribe button down below.